11. A molecule in a gas of temperature 320 Kelvin has a molecular mass m equals 71 grams per mole. What is the root mean square speed? This equation is going to use somewhat our kind of modified ideal gas equation that goes 2 over degrees of freedom equals PV equals nRT. You'll notice they did not tell us what kind of gas it is, but they are asking for a relationship between the root mean squared speed and the temperature. And the reason you can do that, let me write nRT equals degrees of freedom over 2, and I'll expand this U out into its degrees of freedom. First of all, nRT, we're going to have a whole bunch of molecules, n molecules, that is like the number of moles times Avogadro's number. And then our actual U is going to consist of a linear kinetic energy part and rotational kinetic energy part. And this is like a spring constant times an amplitude squared. So we have a spring potential energy part or vibrational energy part. And what happens is if you add these up, you get 1, 2, 3 here, 4, 5, 6, 7. Those are your degrees of freedom. So, and then for this, only 3 of those contribute to the linear kinetic energy. And you know what would help? If I did this 2 over degrees of freedom, as is correct, rather than having it wrong. Okay, now I have been trying to figure out how to explain this, but now I can see that there are however many degrees of freedom you have represented over up here is canceled out however many degrees of freedom you have there, and so you're just left with 2n, and you're left with just 1 degree of freedom, and the energy basically is distributed evenly between those different modes. So we've just got nRT equals 2n times 1/2 m, and this is the RMS velocity, v sub x squared with the average sign over there. That is, well, the square root of that would be the RMS velocity. So let's solve this. nRT over 2n. First of all, let's replace the n here with the number of moles times Avogadro's number. And 2 cancels out with 2. And hey, no. Yes. Mass of a single particle times the number of moles times the number of particles in a mole is actually the molar mass. So you can get that times v sub x squared. Okay, I can solve that nRT for this and divide by n both sides. We get RT over the molecular mass. The only trouble is I've just found v sub x, the root mean square velocity in just one component of the velocity. And the actual velocity is going to be v squared equals v sub x squared plus v sub y squared plus v sub z squared, so which will be equal to square root of 3 v sub x squared. So I just need to multiply this by square root of 3, and I don't know if that's the best explanation, but we just need to put a 3 v sub x, 3 there, and VRMS equals square root of 3 v sub x squared equals, and all that stuff right there. So let's get that equation one more time. V sub RMS is equal to the square root of 3RT over the molar mass, which comes out to 335 meters per second. Sorry that took me a while to get to, but the reasoning may be hard to follow, but that formula does give you answer B right here. Question 12. An inventor develops a stationary cycling device by which an individual, while pedaling, can convert all the energy expended into heat for warming water. How much mechanical energy is required to increase the temperature of 300 grams of water from 20 degrees to 95 degrees? The specific heat of water is 4,186 joules per kilogram per degree Celsius. This is a very straightforward problem. The only issue with this is applying MC delta T as your heat. There's no changes of phase or anything like that. The big issue is changing grams to kilograms because we want to have it in SI, so it's 0.3 kilograms times our specific heat of 4186, and then our delta T going from 95 to, or from 20 to 95 will be 75. And since everything was in SI, once we plugged it in, it comes out in joules. Okay, in problem number 13, we are given a mass of a lead bullet, a speed of the lead bullet, a block of ice of unknown mass, and the latent heat of fusion of the ice. We're to assume that all of the heat goes into melting the ice. They give us the specific heat of lead, but considering that all of the heat generated goes into melting ice, that's just a red herring. And they also give us this figure, 1 kilocalorie is 4,186 joules. And if you're not careful, you'll miss that the latent heat of fusion has been given in non-SI units, which can screw you up a little bit. So the key to this question, we've been given mass, velocity, latent heat of fusion, and we want to find the change in mass of the ice, how much of it melts. So our original kinetic energy is 1/2 mv squared, and we're going to convert that into heat. Specifically, the heat of melting ice is Q equals latent heat of fusion times the amount of mass that is melted. So we're just going to set those two things equal and solve for delta M, which is delta M equals 1/2 mv squared over the latent heat of fusion of the ice. And so, but before we do that, let's make sure everything is in SI units. So in particular, we've got L sub F is 80 kilocalories per kilogram. We don't want that in kilocalories per kilogram, we want it in joules. So I'll put joules on the top and kilocalories on the bottom and use the unit that they gave us, 4,186 joules per 1 kilocalorie. So we can change that to, comes out to be 335,000 joules per kilogram. So plugging that into our equation, we will get 1/2. The bullet was just 3 grams. Our velocity was 240. So we square that. That was in meters per second. And finally, L sub F, we want to make sure that is in SI units as well. So it's 335,000 joules per kilogram. So the answer is 2.6 times 10 to the negative fourth, or about 257.9 grams. I'm sorry, not grams, it's 257.9 milligrams, which is a very small amount of ice to melt. Okay, number 14. For this one, at high noon, the sun delivers 1,000 watts to each square meter of a blacktop road. What is the equilibrium temperature of the hot asphalt, assuming emissivity E equals 1? By the way, this is something that can vary up to like about 1,100 watts, I think, when the sun is directly overhead, to, you know, a lot less when the sun isn't directly overhead. And also, it's interesting to note that here in Galesburg or Macomb, the sun never gets directly overhead. On the warmest day of summer, still the sun is not directly overhead. But if you get between the Tropic of Cancer and the Tropic of, well, whatever the two tropics are, you do find days where the sun is directly overhead. But for our purposes, what we want is the power coming into the road is equal to the power or the intensity of heat leaving the road. That would be what it would look like if things were in thermal equilibrium. And the power coming into the road is 1,000 watts per meter squared. The power coming out of the road is going to be sigma times the area. It's not going to have an area in there. It's just going to be sigma times t to the fourth power. Sigma times e to the t to the fourth. So e in this case is going to be 1, and we can solve that. I'm going to call this 1,000 watts per meter squared the intensity of the light. Intensity divided by sigma e to the power of 1/4. And sigma is 5.67 times 10 to the negative 8th. It's one of your constants. And you end up getting 364.4 Kelvin. And subtracting 273 from that, you get 91.4 degrees Celsius. So the answer there is C. Number 15 is a very similar problem. We're going to be solving for the power output, and we're given the temperature, sigma, and the area, but we're given the area not in SI units, but square centimeters. So our equation is going to be power equals sigma a e t to the fourth. We're going to plug in the given values. We were given sigma, we were given area was 1 centimeter squared. I'll solve for that. E is 0.68, and temperature was 2100 Kelvin. So solving for area, we need to put centimeters on the bottom, meters on the top, so 100 centimeters squared. So that'll be 1 over 100 squared is 1 times 10 to the negative fourth. And plugging in all of those numbers, I got 74.9 or 75 watts.